Okay.
Better. Yeah, that's what I was thinking.
Today we're going to talk about what a dot product is and then how we can apply it to work. Okay. Let's talk about the operations we've done with vectors. We've multiplied a vector by a number. We call it a scalar. We've multiplied by a scalar. We've added vectors, and we've technically subtracted vectors, right? So we're going to call that adding. Have we multiplied two vectors together? No. Okay. That's what a dot product is going to be. There are actually two different ways to multiply vectors. There's a way to multiply vectors and get a vector. There's a way to multiply vectors and get a scalar. Okay, we're going to worry about just a second on that. Okay, and then when you get into upper level calculus, then you can worry about multiplying to get a vector. Okay. So the dot product, we're going to take two vectors, u and v, and I would write them down as u1, u2, and v1, v2, so you can see what we actually do with each component of the vector. So our dot product, like growing up, you learned multiplication, like 1 times 2, you wrote like a little x, right? And then when you got into algebra, you wrote it as the dot, right? Okay, so we're going to notate the dot product with that little multiplication dot. So we call this u dot v, and what we're going to do, u1 and v1 get multiplied together, so the horizontal components get multiplied together, plus u2, v2, the vertical components get multiplied together. I don't care if you write this down or not, but what I need you to understand is that when we take two numbers and multiply them together and add them to another two numbers multiplied together, we're getting a scalar. Okay? This is not a vector, this is a scalar. Alright? When we add vectors together, we get vectors, but when we take a dot product, we're going to get a scalar. Here's the first example that we are going to do. I would write it down if I were you. Vector v is the vector 2i plus 5j, and vector w is the vector 4i plus 1j. So if we want to find v dot w, okay, we are going to take the horizontal components, -2 and 4, multiply them together, and then we're going to add the product of the vertical components, 5 and 1. So -2 times 4 from the horizontal components, and 5 times 1. Those are coming from the vertical components. So, you don't think so? Need some air going there? What's our dot product? -8 plus 5 is -3. Okay, that's all a dot product is. Okay, so I'm going to give you one. In red. Whoop. I'm going to give you that vector u is the vector 2, 1, and vector v is the vector -1, 0. Can you find me u dot v? Find it on your own, and then when you have an answer, compare it to your neighbors to see if yours is the same. When you have an answer, compare it to your neighbors. Well, if you have 3 vectors, then 2 of them will multiply to be squared, and then that 3rd vector will just get multiplied. You understand what I mean?
Yes.
Chad, what'd you get? -2. Do you agree with Chad? Okay. Next thing I want you to think about, in this red example, I asked you to find u dot v, right? Don't answer it aloud, just think about it. Would v dot u get you the same or different answer? V dot u would give you the same or different answers. Okay, Courtney, what do you think? Same answer. Okay, what does it mean if u dot v and v dot u would be the same? What's that property? Ah, yeah, the commutative property. Okay, it doesn't matter the order because we're still multiplying the horizontal components and we're still multiplying the vertical components and adding them together. Okay, so it doesn't matter the order. Okay, now I wouldn't say that you need to write these down. These are in your book if you want to go for it, but these are just some properties. We discussed some properties in the beginning. These all deal with the dot product. Okay, u dot v and v dot u are going to be the same. It does not matter the order in which you do the dot product. Okay. If we take a vector and take the dot product with a 0 vector, what are both of those products going to get you? 0. Okay. So if you take the dot product with a vector and a 0 vector, the product's going to be 0. I feel like that's something that you'd be able to figure out without me telling you anything. Okay. Couple other properties. Distributive property, right? If we have the dot product between u and v plus w, you could distribute that to be u dot v plus u dot w. Okay, it's just multiplication, right? This is the one that I find the most interesting and one that you may want to write down. V dot v is the magnitude of v squared. V dot v is the magnitude of v squared. Let's talk about that. If v is the vector AB, all right, then what happens when we take v dot b? Okay, we would have to take a times a plus b times b. Well, a squared plus b squared, that's just what's under the radical for the magnitude. Do you agree? Okay, so v dot v, if we would square the magnitude, that square root goes away. So the dot product of v in itself is the magnitude squared. Okay. And then this last one would just be, I guess, the associative property. If we have a scalar multiplied to a dot product, remember the dot product is multiplication. We don't distribute into a multiplication problem. We just change the order of our multiplication. So you can take the dot product first and then worry about the scalar, or you can take the scalar times one of the vectors and then do the dot product. Okay? Just the order is different. Okay, so I think we can all agree that the dot product's not so bad, right? fairly simple calculation. What can we do with it? What purpose does it serve? Okay? The main purpose we're going to use it for is to find angles in between two vectors. Okay? We are going to find the angle in between two vectors by using the dot product. Okay? And here is the formula that we are going to use. Okay, so I'll give you a moment to write down what you need to. But this is the formula for the angle between two vectors. Okay. Now, some of you may wonder where this comes from. This formula does come from a triangle made by the two vectors using a law of cosines formula. Okay, I'm not going to go through the proof of that, but that is kind of how it relates back to those first couple sections that we did. Is this formula comes from the law of cosines setup. So what's happening is we're going to have, who knows where these vectors are going to be? Maybe one's here and one's here. All right. Technically, there are an infinite number of angles between those two vectors, would you say? Okay, I think we see two obvious ones, but we can be very obnoxious and say, you know, there could be a 20-degree angle, or there could be a 380-degree angle, or, you know, we can keep going, all right? But what this formula is going to find, this is going to find the smallest angle between the two. Okay, so when we look at that, you guys probably see like two separate angles between the two vectors. It's going to find the smallest one. Okay, your angle will always be between 0 and 180. Okay, they're going to be the closest together. So to apply this formula, we're going to need the dot product up in the numerator and then the magnitude separately in the denominator. Okay. Biggest thing about using this formula is just making sure that you're using your calculator correctly. All right. So make sure you have that out for when we are ready. Okay. Something else. I shouldn't have done my screen share. Okay. If the angle is 0 or 180, that's going to mean our vectors are parallel. All right. If we have an angle of 0, that means they're going in the exact same direction. If our angle is 180, that means our vectors are going in exact opposite directions. Okay. Whether they are going in the same direction or opposite directions, they're still going to be viewed as parallel vectors. Okay. Just wanted to talk about that before we went. Okay. So then we're going to do this example. I believe this is the same example from earlier, correct? The V is 2i plus 5j and W is 4i plus j. This is the example that we found the dot product in, which is nice because we need the dot product, correct? Okay. In order to find the angle in between these two vectors, we need the dot product. Well, we know that the dot product, remind me, was it -3? Yeah? Okay. And then we also need the magnitudes. We need the magnitude of V and the magnitude of W. Okay, so we just have to use that Pythagorean theorem, the square root of a squared plus b squared. So I'll give you a moment to find each of those magnitudes for me, leaving them in radical form. You know, what would the magnitude of vector B be? Radical 29? And vector W, the magnitude of vector W. Grace W, what do you have? Radical 17. Okay, so the cosine of that angle in between is going to be the dot product over the product of the magnitudes. Okay? Finding the dot product, not so bad. Finding the magnitudes, not so bad. We've done it many times before. Okay? Biggest thing here is making sure you're using your calculator correctly. Okay, so I meant to do this before. Okay, so first of all, make sure you're in degree mode. You all should be in degree mode from yesterday, but mine is not. Okay. So if we want the angle, first of all, we're going to have to press inverse cosine. All right? And then we're going to have to press in -3 divided by. We have a product in our denominator. If you do not put parentheses around that product, let's talk about order of operations. Multiplication and division are tied in order of operations. So when you punch it in, it's going to go from left to right. If you do not put any parentheses around that product, it's going to take -3 divided by radical 29 and then multiply by radical 17. That's not what you want. Okay? So make sure you put parentheses around radical 29 times radical 17. So our angle is 97.77 degrees. All right. The next topic we are going to discuss is what orthogonal vectors are. Orthogonal vectors. So the first thing I'd like you to do, you don't know what orthogonal means in terms of a vector, but I'd like you to just brainstorm at your pod what you know about words just from the English language, and see if you can figure out what orthogonal may mean in terms of the relationship between two vectors. Okay, if two vectors are orthogonal, what could that mean? Go ahead and talk.
But the orthos goes that way.
How do you like your keys? Like all the dogs?
Around, oh, is that where you have to see like how many ways you could like cut it? Oh, and then figure out how many like the angle. That's like an equal answer.
So I was just thinking of. Okay, ideas. in your mouth? Teeth, right? And how do we like our teeth to be?
White.
The vectors don't have teeth. Okay, we like our teeth to be white. What else? Straight. Okay? So, if you think about your mouth and how your teeth are, right? Do you want them to be at an angle? What kind of angle would there be between your teeth and your gums? What? All right, angle. Orthogonal vectors are perpendicular. Our vectors do not have teeth.
Will they get downgraded if there's your teeth on them?
Yes. Everyone went right to mouth. Nobody went to like orthopedic. Oh. I know. But that's just, I'm just saying that surprised me that nobody went to like the orthopedics. Everyone went orthodontics. That's true. I'm glad that is true. Okay, so now let's go back to here. Okay? Right angle means 90 degrees. I need somebody to tell me what's the cosine of 90 degrees? What? 0. If we have a 90-degree angle, then that means this big fraction right here is 0. But let's think about it. If a fraction is 0, what specifically is 0? The numerator, okay? So, if our numerator is 0, the entire fraction is 0, right? And if the cosine of an angle is 0, we know that angle could be 90 degrees. So, shortcut, if our dot product is 0, we know we have orthogonal vectors. Because we have the cosine of theta equals 0, theta is 90 degrees. So if the dot product is 0, you can stop and just say, hey, we have orthogonal vectors, our angle is 90 degrees. Okay, so here are two vectors. 2, -3, and 6, 4. You'll get a question like this. Are these two orthogonal? What do I want you to do? Find the dot product and show me the dot product. Don't just say yes or no, okay? Show me, prove to me yes or no that they are. So our dot product, we're going to take 2 times 6 and add it to -3 times 4. What is that? 0. Yes, they are orthogonal. The angle between the two vectors is going to be 90 degrees. Okay. Last topic, work. Those of you who have had physics, can you tell me what work is? Have you done work in physics? Yeah? Do you remember how to find work? Thank you, Chris.
Force times distance.
Yes. Work is force times distance. Okay? Now, in physics, you say displacement, right? So if you would like to write displacement, that is fine. The book for free calculus calls it distance. we're always going to go forward. Right? Okay. Now, work equals force times distance. Okay. If I were to take Eli and I were to lift him up, okay, I'm pretty sure I think they would do it. Okay, let's say Eli is like, what, 150 pounds?
Yeah.
Okay, 150 pounds. So if I take Eli and I lift him up 2 feet, then I am exerting 300 foot-pounds of work because he's 150 pounds and I lift him 2 feet off the floor. Okay. Now, what if I'm pulling a wagon? Okay? I pull a wagon all around the zoo, hills and everything. Probably not anymore, my kids are out of school now. But if I'm pulling a wagon, I'm pulling it at an angle, right? But if I'm pulling a wagon, what direction is it moving? Horizontal, right? It's not moving vertical. So even though I'm pulling it at an angle, it's only moving horizontal. So only the horizontal component of force is acting on the wagon. Okay? And that's where vectors are going to come in. If we are applying force at an angle, but our object is moving only horizontal or vertical, then only that component of force is actually acting on the object. Okay? So here's our example. And this is actually number 72 from your book. So if you just want to write number 72 and not have to write down all of the words, that may help you. Okay. But what we have is we have a tractor pulling a log. Seems reasonable. 800 meters. And the tension in the cable connecting the tractor and log is 1,600 kilograms. The cable is at a 35-degree angle. Okay, so this is what's happening. We have a tractor. Guy driving the tractor. Okay? The tractor is pulling a log. At a, what, 35-degree angle? With 1,600 kilograms of force. Okay. And he pulls it a distance, okay, of 800 meters. Okay. So this is how we find work. Work is force times distance, or force times displacement, whichever word you would like to use. Now, what direction is the log moving? Is it moving at a 35-degree angle? No, it is moving horizontally, right? So the only force that matters here is the horizontal component of force, okay? So instead of a force of 1,600 kilograms, we are actually talking about 1,600 kilograms times the cosine of 35 degrees, because that would be the horizontal component of force. And then our displacement of 800 meters. Okay, so please help me out. What is 1,600 times the cosine of 35 times 800? Don't forget to close your parentheses off after the 35 degrees. It's a pretty big number, isn't it? Nick, what do you have?
1,040,514.62.
Okay, and we took force in kilograms and multiplied it to meters, our length, our distance in meters. So our label is literally kilograms times meters. Yes. Not unless it's moving vertically. Okay. So trying to think an example where that would be. Like if I'm pulling at an angle and my object's moving vertical, then the vertical component would matter. Okay. But I can think of a lot more examples of horizontal movement, like pulling things, right? That we're mostly going to see in here. Yes. I used cosine since we are worried about the horizontal component of force, right? Because it's moving horizontally. Okay. Anything else? Your pictures don't have to be as fabulous as mine, okay? I know that tractor is like, I would draw a picture, but I mean, look at mine. That's the most ridiculous tractor I've ever seen. But it at least pays the picture. I haven't seen her. Okay? It's not our class. Just get an idea of what's going on. Okay? All right. I think that's all I have for you. Look at that.
Just a square and the word tractor.